Okay, let's take a look at how to construct a confidence interval for proportion. Okay, so let's take a look at this problem here. Dental visits. In a survey of 674 U.S. males aged 18 through 64, 396 say they have gone to the dentist in the past year. Okay, so the instructions are to construct a 90% confidence interval and a 95% confidence interval. Okay, so let's go ahead and review the formula for the confidence interval for proportion. Okay, so it's p hat plus or minus z sub c times the square root of p hat times q hat over n, where this part here is the margin of error. And p hat, right here, p hat is the number of successes out of our sample size. Okay, and if you read through the text, we can go ahead and use the normal distribution to approximate the binomial distribution if n times p hat is at least 5 and n times q hat is at least 5. Okay, so if p hat is x over n, q hat would be 1 minus that. Okay, so you might have a few homework problems where you have to check the assumption of normality for this part here. Okay, we're just going to go ahead and assume that's been met. Okay, so given in the problem, we're told that n was equal to 674 and x was equal to 396. Okay, so we're calling a male going to a dentist as a success. Okay, so pretty straightforward to calculate p hat. So p hat is going to be 396 over 674. And I can go ahead and convert that to decimal. Okay, and I get, and I want to carry it out a bit far. Okay, so it's going to be approximately 0.5875. Okay, so q hat will be 1 minus that, 1 minus p hat. Okay, so I'm going to subtract that from 1. Okay, so I'm going to get q hat's about 0.4125. Okay, so now I have most of the pieces I need to input into the formula. I have p hat, q hat, and my sample size of 674. Now I just need the critical value. Okay, so the critical value is going to come from the z distribution, and I want to do it for a 90% confidence interval first. Okay, so just like before, in section 6.1, I'm going to draw the normal distribution, put 0 in the middle, and partition my bell curve to have 0.9 amount of area between these two critical values, and we only need the upper critical value for the confidence interval formula. Okay, so one way to do this is I could recognize the fact that since I have 0.9 amount of area between these two symmetric values, I'm going to have 0.05 area here, 0.05 area here. So cumulatively, I have an area of 0.95. I would need that to use the calculator to find the upper critical value. So I could go inverse norm. Okay, again, this is nothing new at this point. We did this in section 6.1, and also it's in chapter 5. Okay, so inverse norm 0.95. Okay, so I want to go to my distribution menu and select inverse norm. It's expecting a cumulative area of 0.95. Okay, so I have a critical value of 1.645. Now remember, if we look at our z table, let me find that page. There we go. Our table has common levels of confidence down at the bottom. So a quick way to get that critical value is I look for my common level of confidence of 0.9, and it gives me that critical value, the upper one, of 1.645. Okay, so however you want to do it is fine, as long as you find the correct critical value. Okay, so now I can plug and chug. Okay, it's going to be 0.5875 plus or minus 1.645 times the square root of 0.5875 times 0.4125, it's kind of a big radicand, over 674. Okay, so I just inputted directly into the formula, and this part being the margin of error, so I'm going to go ahead and find that part in case you needed it separately for the homework. I will be going and doing this in the calculator directly. There is a one proportion z interval built in, but I just did want to take the time to go over this by hand. Okay, so I'm going to put the radical part in first. Definitely want to observe order of operations. Whoops. Okay, so square root of 0.5875 times 0.4125. Close that parentheses. I'm still under the radical, and I want to divide that product by 674. Okay, I want to arrow out of that. Okay, and that's just the radical part. And then I want to multiply that. Sorry. I want to multiply that, not divide, by the critical value of 1.645. So I'll get a margin of error of about 0.0312. Okay, so that's the part I need to add and subtract from my point estimate for my proportion of 0.5875. Okay, so doing that, 0.5875 plus minus 0.0312. Now I've done some rounding in between. Okay, so when we take a look at this one directly in the calculator, it may be the case that we're off a smidge, okay, due to rounding. Okay, but let's see what we get. So I'm going to subtract first. Okay, and I'm going to round to 3 decimal places. I think the textbook mentions that they round to 3 decimal places for proportion. Okay, I'm not exactly sure if they changed that a bit in my stat lab, so you want to round as you're instructed there. Okay, so 0.556 up to about 0.619. Okay, so that's going to be a 90% confidence interval for P. Okay, the true proportion, or the population proportion of adult males who have gone to the dentist in the last year. Okay, so let's go ahead and get this in the calculator directly. Okay, so what I want to do is I want to press my stat key. Okay, I'm going to go to the same place, same screen that I got my confidence interval for the mean. Okay, the z interval and the t interval. I want to go to tests, and then I want to scroll down to one proportion z interval. Okay, it takes a little while. There we go. So one proportion z interval. Okay, the calculator doesn't give any other option except to use the z distribution to approximate the binomial. But you're going to be fine. You won't run across a problem where that assumption has not been met. The assumption being n times p hat and n times q hat have to be at least 5. Okay, so I'm going to select one proportion z interval. Now it's going to be expecting an x value. Okay, so I think the calculator expects whole numbers here. In StatCrunch you can put in fractional values, which is really nice. Okay, but for this problem we had a nice whole number. Okay, we had 396. That was the number of men who have said they went to the dentist in the past year out of a sample size of 674, and I want to change my level of confidence to match the problem, okay, 0.9. Okay, so here's what we get. Okay, so the calculator is a bit more accurate. Now remember, I did do some rounding in the intermediary steps. Okay, so my lower limit from the calculator, if I round to 3 decimal places, is the same as what I got. Okay, so 0.556. And then the upper confidence interval limit, rounding to 3 decimal places, is 0.619. Okay, so I know the calculation is a bit cumbersome here. You are welcome to use your calculator or StatCrunch to find these. Okay, but if you want to do things by hand, this is how the formula would work. Okay, and then they also ask for the 95% confidence interval for P. Okay, I'm going to go ahead and just do that in the calculator. What would change if I wanted to do the formula is this critical value. Okay, everything else would be the same, but I would have a different critical value. Okay, that critical value would be a bit larger than this because I am asking for a higher level of confidence. Okay, so let's go ahead and get this in the calculator. So I want to go back to my stat menu, right arrow over to test, and then scroll down to the 1 proportion z interval. And now I'm just going to change my level of confidence to 0.95. Okay, so from the calculator, I get a confidence interval of 0.550 up to 0.625, and that's a 95% confidence interval for P. Okay, so like section 6.1 and 6.2, if we increase the level of confidence, the width of the confidence interval also increases. Okay, that's always true for confidence intervals. Okay, so keep in mind when you're doing the formulas, what's going to change if you change your level of confidence is that critical value. A higher level of confidence will cause you to find a confidence interval that's further away from the mean.